Okay, so I'm Anders, and first time I talked about OPA ever was at this conference 5 years ago. And I'm here still talking about OPA, so I guess I haven't done much since. But that's pretty much how I first got involved in OPA, or how it all started. I didn't know much when I submitted a talk. So I was rather terrified when it was accepted, and I had like a month or two to learn this technology. But that was a good way to learn, though. These days, I don't think there seems to be a lag here. Okay, so these days, I lead developer relations at Styra, which is the inventors or founders of OPA. I have a pretty long background in software development. And I've also worked at Curity, actually, and I've worked with identity systems. So that kind of brought me into authorization and how to solve that problem. And when I'm not at work, I'm also a maintainer of 2 kids. And if you want to reach out, I'm available, just my first name, followed by my last name. So we just heard a talk about authorization. So I figured, like, distributed authorization, that would be my kind of angle on this. So how do we do that? It's pretty complicated. So I figured a good way, since my background is in identity, I figured like that is a good way or a good place to start out from. So yeah, I'm sure you all experienced this transition from monolith services to microservices, where it's basically all the same features or components, just broken up into multiple services. The 2 services of interest today is going to be authentication and authorization. So a fairly simplified model, but essentially identity in the monolith application works something like this. A user presents some credentials to the application. The application goes to the user database, verifies the credentials. Eventually, if that checks out, verifies the permissions. Is the user allowed to access this data? And if that checks out, the data is returned to the user. So basically, one application to handle everything. Authentication, access control, and data retrieval. So if we were to just break this application up into many pieces or many services, a naive model would look something like this. We'd have the user present their credentials. The credentials are passed around between all these services, and all these services will need to look up the identity of the user, and they will need to do a lookup for permissions. So as you can see, there's a whole bunch of arrows pointing everywhere here, and that's not a very scalable model. So yeah, so there's a couple of issues here. Like obviously all these arrows, as mentioned. Another issue is, of course, this passing around credentials to services that should probably not be involved in that at all, and having credentials end up in logs and so on. So the first step in this evolution of identity is, of course, this decoupling that the previous speakers talked about this too, where you decouple identity to an external system, an identity system. So rather than the user going to the service to verify or to present their credentials, they go to the identity system. And in return, they get back a token. And that's passed around between all of these. And of course, not only users need to identify themselves, we need some way for other machines or API clients and so on to do this. So another benefit of an identity system. So if everybody needs a token, how do you get one? And that's basically what OAuth 2 describes, how to obtain tokens. It doesn't say what the token is. That's left as an exercise for the reader or for the implementer. It's rather about delegation than authorization. There's some very crude or coarse-grained authorization baked in the form of scopes, but not much more than that, which is ironic given that it's called like an authorization framework.
So that is basically how you obtain a token. But we still don't know who is this user. That didn't give us an identity, it just brought us a token. And that's basically what OpenID Connect did. They added an identity layer on top of OAuth, so that you can say that a user probably has an email address, an ID of some sort, and so on. And it also added a bunch of extra ways of obtaining this token, assuming that the user is a human. And by doing this, we have a way to federate identities. So you can go and log in on your Google account and have that identity federated across other systems. So what is a token? I'm sure you've all heard of like API keys. That's the way we used to deal with tokens. And the problem with these, or like opaque tokens, where you just say like a token says ABC 1, 2, 3. What does that mean? If you get a token like that, what does that mean to you? Like, it doesn't mean anything. So that model doesn't really scale very well. Because in order to know what ABC 1, 2, 3 is, you'll have to go back to this identity system and ask it, what does that represent? And it might tell you, like, this is a user, and it's a valid one, so you should allow this. But should all these services validate this? Then we're kind of back to where we started, where we have all these arrows pointing. We just got rid of a database, but we essentially made the identity system a new one. So pretty much the point of JSON Web Tokens is that we should have a means to avoid this. Because when the tokens are self-contained, it means like they have all the data, all relevant data is contained inside of the token. It's signed by the identity system, the issuer, and can be verified by all the recipients or all these services. So there's no longer a need to go back and ask, what does this mean? Just look into the token and verify that it's valid. And yachts have a few common claims, so you can check that it's not expired, you know that the issuer is one you trust, so on. So we have a good way of carrying identity across our systems. One thing to consider is, of course, that again, anyone can open this JSON Web Token and see what's in there, meaning it might be a good idea to not carry that outside of your systems, because that's an information leakage. So a good kind of pattern is to have opaque tokens, like these ABC 1, 2, 3, outside of your clusters, and then have them exchanged for something meaningful inside of your clusters. OK, so that is basically distributed identity solved. What about authorization? And that takes us into the evolution of access control. As you can see here, we still have a few arrows to address or to remove. We still don't have a truly scalable system, because even if we have verified the identity of the user, we can't tell just by looking at this token. It's basically a passport. And this passport is not going to tell me if I can go to the United States or some other country. That is up to that country to decide. It's not part of my identity. And that's basically what authorization is, right? So a few problems with this, all these lookups, and it also means that we'll need to embed authorization logic in all these services. And these services can be written in all kinds of languages. So it might mean that we need to have like different copies and different versions, potentially written in different languages of the same authorization logic. So if we want to change that logic, that's going to be tough. So where should we do authorization? And and in the previous talk, they talked about the gateway model. And that's been like a prevalent model for where to do authorization for the past decade or so. And it does work fairly well. It means you do authorization at the perimeter. So you put a gateway in front, and you say, like, hey, should this request be allowed or not?
And if you only do authorization there, it's going to be fairly fast, because there's just one of these arrows now that needs to go back to the database or whatever authorization system you have and check, should we allow this or not? Of course, as with any of these centralized systems, it's a central point of failure, or a single point of failure. But more problematic is, of course, is this secure enough? Because obviously, if you make it past the gateway, if you say that that's the only place where we do authorization, and you make it past that, it's basically an open highway. There's no more checks after that. So recently, we've come to talk about the zero trust model, which basically means no service should make any kinds of assumptions. Because in the gateway model, all services assume that there's a gateway in front that took care of authorizing the user or authorizing the request. That's not an assumption that we can afford in the zero trust model, but everybody needs to verify identity. Everybody needs to verify authorization. But again, we're not getting rid of these arrows. If we all have to do it somewhere and we store permissions somewhere else, we're still going to have to do all these external checks. So if we have thousands of these services and they're all going to have to do these checks all for every single request, that's going to be very costly. So we're basically back to the naive model where we started. So how would you improve this? And here's one simple trick that I don't want you to know about. And the first simple trick is basically this. I don't know if you noticed the direction here of the arrows. So rather than having all these services call out to the database or to the permission system, you have the permission system distribute the data that these services need beforehand. So it's in memory and available to the services at the time of the request. It might mean that the data is somewhat stale, because it might not be up to date the second that request comes in. But this is a scalable model, so even if the data is a few seconds old, that's probably tolerable in most systems. So this is a good start. So a next problem we should probably need to face is this: like, what if all these services? And this is not just hypothetical. I have worked in exactly this environment where we had services in 7 or 8 different languages. So how do you solve authorization in an environment like that? There's really no common ground. You'll have to have a team write authorization logic for all these languages, and then how do you handle updates? How do you handle auditing? Because all these frameworks are going to log authorization in some different way, and some different format. So how do you know like what actually happened in your environment? That's basically what Open Policy Agent helps you with. So OPA is an open source general purpose policy engine. As David said, it's not just for authorization. You can create any kind of policy, and then you query OPA for decisions. It's a unified toolset and a framework for working with policy across your whole stack, which decouples policy from application logic. So meaning even if you have services written in all these different languages, that's no longer the responsibility of those services, because that's been decoupled. And I think it's in the ABAC terminology, we heard about the policy decision point, which would be OPA, and then the policy enforcement point, which is your service. These policies are written in a declarative language called Rego, which I'll show you in a bit. Outside of authorization, there's a whole bunch of kind of popular use cases. Kubernetes admission control, like should this pod be deployable, given that it doesn't have a secure configuration? Microservice authorization, any kind of infrastructure, Terraform, and so on. But all kinds of use cases, data source filtering, CI/CD pipelines, and so on. So it's truly a versatile tool. And how does it work then? the policy decision model is fairly simple. It's basically this. You have a service taking in a request, and when we say service, again, a broad definition could mean anything, really. That service, instead of providing an answer itself, queries OPA for a decision, and the query is just JSON, and the return or the output is also just JSON. So anything that can handle JSON can basically work with OPA. And OPA is a self-contained, lightweight binary. So I think it's like 40 megabytes or something. So you can basically deploy that anywhere. And ideally, you deploy it as close to your applications or services as possible. So it's not one big monolith. Again, that's the model we're trying to avoid. And applications commonly work with OPA through its REST API, but there's a whole bunch of other ways to integrate OPA. So on Rego, I'll just skip through here to get to the demo, and I think that will be a better demonstration of Rego. But basically, you have a policy. A policy consists of a number of rules, and you can work with these rules like you would with any programming language. So you can have unit tests, you can have linters, and so on. And that's where we're going to try now. I'm just going to show you quickly what a policy might look like. And can everybody see this? Is this big enough, or should we make it? So first off, we said input is just JSON. So this, for a REST API or a microservice, it might look something like this. You have a request. It's a GET request. Somebody is requesting to see the user Anders. And this user making the request is Peter. And he has a few roles here. So by default, we might want to say that we should not allow anything. That's a sensible default. So, but allow if, and now we start to write our rules here. So if the input request method is equal to get, and the input request path, or the first path component, is user. So anybody should be able to read any user. That's the rules of this system. Might make sense here. So we have a GET request, and the first path component is users. So if we evaluate this, we see that it is true. We are allowed to do this. And if we change something here, so we make this a put request, we should see that we're no longer allowed. It's false. So if we want to make this slightly more advanced, we might add another rule, which says if the input request method is equal to put, then the path, the first, oh, sorry. So then the request path should match the ID of the user. So basically what you see here, Peter needs to be matched in the path. So I should not be allowed to modify somebody else's information. But if I change this here, if the user or Peter tries to modify his own information, that should be allowed. So that's a very simple example of policy offering. I think we're running out of time here, so I'll skip back. OK, so now we got OPA running next to all of our services. They get a request. They'll send in a JSON document like this. OPA will make that decision. Policy decoupled from application logic. So the last little change here, or improvement, is, of course, databases are not really meant to distribute data or policies like this. That might be where the data or policies are stored, but it's not the responsibility of a database to do this. So in a real-world system, that would be what we call a control plane, where kind of manages permissions from data sources, manages permissions, and distribute those to services. And that's basically what Styra, my company, provides. So with that, we have solved the problem of distributed authorization. So if you're curious to learn more, there's some good docs at the Open Policy Agent site. There's a Slack channel. There's a playground where you can try this out. Styra also has good documentation. There's a cheat sheet, a linter, and so on. So try it out. Thank you.